welcome to another module in this massive open online course on Bayesian MMSE estimation for wireless communications. So, we are doing an example to illustrate the derivation of the LMMSE equalizer, alright, and we have considered or we have demonstrated that this matrix PDH H transpose plus sigma square identity, that this matrix is, well, this matrix is given as, let me just write this down clearly, this matrix is, it is a 3 cross 3 matrix with a 6 2 0 2 6 2 0 2 6, okay. And now we have to compute the inverse of this matrix. We have to compute inverse of, to derive the LMMSE equalizer, we have to compute the inverse of PDH transpose plus sigma square identity, this matrix inverse, okay. Now, what we have to do to compute this inverse, first we have to compute the determinant. First we have to compute determinant in order to compute the inverse of this matrix. Alright, so previously whenever we computed a matrix inverse, we considered 2 cross 2 matrices, but this is a 3 cross 3 matrix. So, computation of the inverse is still possible, but slightly more involved. Alright, so the first step is to compute the determinant. Okay, so let us start by computing the determinant, that is the, let us denote the determinant by DET. Okay. DET of this matrix 6 2 0 2 6 2 0 2 6, and this determinant is also denoted by this symbol. Sometimes the determinant is also denoted by this kind of modulus sort of symbol. Of course, modulus is for the real numbers, and this, so this is your modulus symbol, which is also used to denote the determinant of a matrix. This is also, and we will also employ this is also, we can explicitly write the determinant or this modulus symbol also employed for determinant of the matrix. And now, if you look at the determinant of this is nothing but 6 times 6 into 6 36 minus, so this minus 6 into 6, you can see, you can refresh your knowledge about the computation of determinant of 3 cross 3, 6 into 6 36 minus 2 into 2 plus, considering expanding along this column, plus 2 times, well, 2 into 0 minus, that is 2 into 0 minus 2 into 6, that is 12, plus 0 times, of course, whatever this is, it does not make any difference because it is multiplied by 0. So, net this will be 6 into 36 minus 4, that is 32 plus 2 into 0 minus 12, 2 into minus 12, that is basically your 192 minus 24, and this will be equal to 168. Okay, so this is the determinant of. So this is your determinant of this matrix PDHH transpose plus sigma square times identity. Okay. Now we have to compute the inverse of this matrix. So we have to divide the inverse of this matrix is given by 1 over the determinant of the matrix times the cofactor matrix. Okay. So that inverse is basically PDHH transpose plus sigma square identity inverse is equal to 1 over the determinant, that is 1 over 168 PDHH determinant of this matrix times the cofactor matrix. Again you can refresh your knowledge about the cofactor matrix. For example, if you look at this matrix PDHH transpose plus sigma square identity, PDHH transpose plus sigma square identity, which is equal to your 2 or 6 2 0 0 2 6 2 0 2 6. For instance, cofactor of 6 equals, that is equals your 6 into 6 minus 2 into, that is 36 minus 4, that is equal to 30, that is equal to 32. Similarly, the cofactors can be, for instance, cofactor of 2 equals, this cofactor of 2 equals 2 into 0 minus 2 into 6, that is 2 into 0 minus 2 into 6 equals minus 12. In fact, these cofactors are nothing but what you multiply the corresponding element by to get the determinant, alright. So, you can look into this thing if you are not familiar with this, it is very simple. So, basically to compute the inverse we need to compute 1 the determinant and 2 what is known as the cofactor matrix, okay. And the cofactor matrix for this is given by the matrix of cofactors the cofactor matrix is 32 minus 12 4 minus 12 36 minus 12 4 minus 12 32. This is the matrix of cofactors, okay. And therefore, the inverse HH transpose plus sigma square identity inverse is basically 1 over the determinant, that is 1 over 168 times the cofactor matrix, that is 32 minus 12 4 minus 12 36 minus 12 4 minus 12 32. This is the required inverse, okay. So, this is basically your PD HH transpose plus sigma square identity inverse. Of course, you can take 4 common out of this and you can simplify it, but we can do it later, right, okay. Now, we need to compute further. Next, we need to compute, for computing the equalizer, this quantity PD H into this 1 bar 2. To compute this equalizer, remember that is given as the product of two quantities One is this well, the equalizer vector, remember, is equalizer is basically this PD HH transpose sigma square identity inverse into PD 1 bar 2 transpose times H transpose. I think this is, there is an error over here, this is simply H times 1 bar 2, this is simply H times 1 bar 2, that is the transpose of this vector transpose of this vector above. Okay. So, now let us compute this quantity over here, PD times H into 1 bar 2, that is equal to, so PD times H into 1 bar 2, that will be equal to your, well, PD is 4 times H, which is 1.5 0 0 0 1 0.50 0 0 1.5 times 0 0 1 0, which is equal to 4 into 0.5 into 1, which is equal to 0 to 4. Okay. And now, therefore, the equalizer, now we need to compute the equalizer vector C bar such that C bar transpose Y bar K, remember that is your net equalizer, that is the net implementation of the equalization process. Okay. So, the equalizer vector C bar, therefore, C bar is given as, equalizer vector is given as C bar equals PD H H transpose plus sigma square identity inverse into H 1 bar 2 into, of course, this is a scalar constant PD. So, we can, this is the power of the symbols, we can bring this outside. By the way, this is your vector 1 bar 2 0 0 1 0, this is the vector 1 bar 2, which basically has 1 in the second position, all 0, basically all 0 except one in second position counting from 0. Except one in second position counting from 0. Okay. So, now therefore, this will become PD. So, now this will become PD H H transpose plus sigma square I inverse into PD H into 1 bar 2. So, this is 1 over 168 times 32 minus 12 4 minus 1236 comma minus 1236 minus 12 into 4 minus 12 into 32 into 0 to 4, and if you look at this, this will be 1 by 168 times minus 8 24 104, taking I think 8 common, this will be, well, minus 1 divided by 21, 3 divided by 21, 13 divided by 21, this is your C bar, which is the equalizer vector. Okay. So, this is your C bar, which is the equalizer vector C bar. So, your equalizer vector C bar has been derived as -1 over 21, 3 over 21, 13 over 21. This is the equalizer vector. Alright, we have basically substituted all the quantities, used it in the expression that we have derived previously for the equalizer vector. Now, the equalizer has to be implemented using this equalizer. Remember, the equalizer is nothing but equalizer performs nothing but the estimate of the symbol x k. It yields the estimate x hat k. X hat k is C bar transpose y bar k. Okay. So, equalizer is, so net your LMMSE equalizer is x hat k equals C bar transpose y bar k, that is, which is equal to, now C bar we have derived above. So, C bar transpose is nothing but column vector gets converted to row vector, that is minus 1 over 21, 13 over 21, 3 over 21, 13 over 21. 13 over 21, this is your C bar transpose, and your y bar k is nothing but y k plus 2, y k plus 1 and y k, and therefore, x hat k equals minus 1 over 21 times. So, the net equalizer is C bar transpose into, this is your y bar k, which is minus 1 over 21 into y k plus 2 plus 3 over 21 into y k plus 1 plus 13 over 21 into y k, and this is basically x hat k, and this is finally what is your LMMSE equalizer. This is your okay. So, this is basically your LMMSE equalizer. Okay. So, once we have derived this vector C bar, the LMMSE equalizer is simply C bar transpose into y bar k, and that yields the equalized estimate, that is x hat k, in order to remove the intersymbol interference, or basically ISI removal in the wireless channel. Alright. Okay. Now, the error, also the LMMSE equalization error, we have derived the expression for the LMMSE equalization error, and this LMMSE equalization error, that is given as PD minus PD into 1 bar 2 transpose H transpose PD H transpose plus sigma square identity inverse into PD H bar into 1 bar 2. But now see, this part is simply your equalization vector C bar. So, I can write this also as PD minus PD 1 bar 2 transpose H transpose into C bar, and both these quantities we have computed previously. We have computed PD 1 bar 2 transpose H transpose. In fact, we have computed the transpose, the column vector of this. We have computed PD into H into 1 bar 2. So, PD into 1 bar 2 transpose H transpose is nothing but the transpose of that quantity. All right. If you just to remind you, this is basically your PD into H into 1 bar 2. So, PD into 1 bar 2 transpose H transpose is simply the transpose of that quantity. So, therefore, we know all these quantities. So, this is basically simply your PD, which is 4 minus PD into 1 bar 2 transpose H transpose, that is 0 rho vector 0 to 4 times C bar, which is your equalizer vector, and the equalizer vector is basically nothing but that is something that we have just derived, minus 1 by 21, 3 by 21, 13 by 21. So, this is 4 minus 6 by 21 minus 52 by 21, and that is equal to 84 minus 58 by 21 equals 26 by 21, and this is nothing but your LMMSE equalization error. Which is basically, again, to define it more precisely, this is your x hat k, expected value of x hat k minus x k whole square. Okay. So, this is basically your LMMSE equalization error. Okay. So, what we have done in this example is basically we have completed this example of deriving the LMMSE equalizer. Alright, first derived the LMMSE equalization vector C bar, then derived the LMMSE equalizer, and also finally derived the error of LMMSE equalization. Remember, this is for the specific case of your intersymbol interference channel, that is yk equals h0 times xk, that is h0 is 1. So, yk is xk plus 0.5 times xk minus 1, h1 is 0.5 plus vk, where vk is the noise. We have derived a 3-tap equalizer considering the various quantities for this intersymbol interference channel. And as I have said previously, this can also be extended for other scenarios, more general scenarios with a larger number of channel taps and with larger number of equalizer taps. Alright. So, we will stop this module here and continue with other aspects in the subsequent lectures. Thank you.